let me end the poll. Okay. So, okay. Are you able to see the results and the correct answers? I hope you're able to see those. So, you can see the first thing is we talked about the no cloning theorem yesterday, right? And the way we showed that the no cloning theorem, the way we proved no cloning theorem was using linearity of quantum mechanics, right? That was the main feature of quantum mechanics that we use. For example, we use this unitary operator. If you recall, we use the unitary operator on, let's say, phi 1 times the tensor product with psi, right? That gives you the same state phi 1 copied into phi 1, and the device goes into starts with an n particle state. That is, the device has n particles, but it puts out one particle which is copied into phi 1 state, right? And then so you get psi 1 prime or something like that, right? A different state. Similarly, we could do it on phi 2, right? And then you would get,
Professor,
yeah.
sir, your notepad is not visible.
Oh, okay. Sorry. My bad. How about now? Yes, it's
Yeah,
seen now,
fine.
right?
Yeah,
Okay. So phi 2 cross phi 2 cross some psi 2 prime, right? This is what we have seen yesterday. But when you look at a superposition, right, then we saw that if we did this on a superposition, right, then you won't get where phi s is something like 1 over square root 2 phi 1 plus phi 2. We saw that both results do not match. That is, if I use the linearity and apply the unitary operator on phi 1 and phi 2 separately as, sorry,
నీట్గా రాయడానికి ఉంటుంది అది ములుకు సన్నగా ఉంటుంది అన్న అందుకని నీట్గా రాయడానికి ఉంటుంది. క్లాస్
okay. I think there was some disturbance there. But the point is that when you do the U operator on this versus directly on phi s, then you see that you get different results. So we saw that unless phi 1 and phi 2 are orthogonal, those relations contradict with each other. And so therefore we said that we cannot clone an any arbitrarily clone a quantum state. So the answer is no. It is because of the linearity of quantum mechanics. I hope that makes sense. Any questions on that? Okay. The second question is, can a single shot measurement determine a quantum state? No, because a single shot measurement gives only one sample and it doesn't give you probabilities, right? So even no matter what the interpretation is, it cannot tell you the wave function. Even if you use Copenhagen interpretation, it cannot give you the quantum state, right? It can only give you a particular result. That is, for example, if there is a particle and I measure its position, what I will get is its position, right? But not the probability distribution. Irrespective of whether it is Copenhagen interpretation or ensemble interpretation or any interpretation, single shot measurement cannot determine a quantum state, right? So you need to have multiple measurements because quantum state has to do with probability distribution. I hope that is clear. And so 3 people or 4 people who answered incorrectly, please check that. Then the next question, I think there is a lot of confusion here, probably because now I added ensemble and statistics in multiple choices, in multiple options. So in a Stern-Gerlach experiment, if we block all but one output beam, that is considered state preparation. Why? Because it is because irreversibility discards unwanted outcomes, leaving only one desired state. So this was also related to, I think there is one question from Shafna, the first question that was preparing a fixed state from arbitrary input requires irreversibility. Why is irreversibility required? That is because we are trying to, so when we want to make a state preparation, right, when we say we're preparing a state, what we want to do is, irrespective of where we start from, we want to come to one thing, right? So for example, if I have a bunch of silver atoms that are coming through, I collimate them and I put them through a Stern-Gerlach experiment and I cut a slit out and all the particles are coming out here. There is no way to tell what was the state of this up particle here, right? I cannot go back. That is, if I put this back through the Stern-Gerlach experiment, I don't get the same state on the other side. You see what I mean? That is, if I put it from left to right, I get spin up. But now if I send this spin up back, then I don't get back the state that it was in. So I lose all the information that it had. So because I lose the information, that means it is irreversible. If you keep the information, then that is reversible. But if you lose the information, then that becomes irreversible. So that's why when we are filtering out, so when you say filter, it is a irreversible because we are mapping many different things into just one thing. And the information in between is lost. So by taking it back through the Stern-Gerlach apparatus, we're not going to get that information back. I hope that makes sense. Any questions on that?
No, sir. Thank you, sir.
Okay. I think a lot of you did not answer it correctly. So please go back to yesterday's slides and read about irreversibility and why that loss of information, why we need that irreversibility to prepare a state. Okay, let's look at the next state. Next question: how is filtering different from a single measurement on one particle, right? So, when you filter, what we get is an ensemble of identically prepared systems for future measurements. So filtering is not single particle, right? So it's always identically prepared systems for future measurements. And here we need to talk about what a state is. State is, it is encoding information about all probabilities, not just about spin. If I measure energy, the state should encode probabilities about energy. If I measure momentum, it should encode probabilities about momentum. So it is not just encoding probabilities about just the spin. It has probabilities about everything, right? So the right answer is it produces an ensemble of identically prepared system for future measurements. So identically prepared meaning that I know that I am only filtering out spin up particles, but I don't know about, let us say, what is it spin along y-axis, or what is it spin along z-axis. I do not know. I am only filtering out spin along x-axis, or I do not know what is its energy. I do not know what is its momentum, right? So I'm just preparing an identically prepared system, multiple atoms that are coming out of the slit that are exactly going through the same Stern-Gerlach apparatus. So I hope that is clear. There is no collapse because it's not a single particle. We have an ensemble and we have identically prepared systems. Any questions on that? Okay. So then let's look at the next one. Suppose a Stern-Gerlach apparatus filters a beam into up Z state. To determine the state experimentally, are repeated measurements required? The answer is yes, right? Because state, again, which is the next question, right? Which is the best, which statement best defines the state, right? So a lot of you have answered that a quantum state is the specification of probability distributions for all observables. But when I filter out from a Stern-Gerlach experiment something into spin up, right? This is like spin up only, I know only along one axis, whatever. Like if this is x-axis or z-axis, I know that it is spin up along that particular axis. That's all I know. I do not know the probability distribution of, for example, now if I pass this through, let's say, a Stern-Gerlach apparatus along y-axis, I don't know if it will come out as up or not. Whether it may come out as up or down. Right? So I do not have any information of the probability along the y-axis or x-axis or about other observables, whereas quantum state is a specification of probability distributions for all observables. So if you want to measure the complete state, then you have to measure in all bases. We discussed this yesterday towards the end of the lecture, so you may want to go over those slides that even though you have filtered only along one direction. And a quantum state is the specification of probability distributions for all observables represented by an ensemble. This gives us only like one measurement, right? So it is it is not sufficient to determine the state. I hope that is clear. With that, I think that's it for our quiz. I would like to stop here and ask first if there are any questions or confusions on the quiz. Are there any questions on the quiz? Okay. No. Okay. Okay, if there are no questions on the quiz, then I guess Shafna, I think I answered your question. Satvik, you said you had two questions. So do you want to unmute and ask?
Sir, if we have time, I had a question on how do you how the on the last in the last day, sir, you took an example of a cyclotron like looking an apparatus, and I was thinking that the histogram that we get in the end of probabilities, do we call that histogram the wave function?
So the wave function encodes information about that histogram. That histogram is probability distribution, but the wave function is only probability amplitudes. It's not the probability itself. So it does encode the information about that histogram, but it is not directly that histogram.
Okay, so, sir, in some time, if possible, would we talk about how do you construct actually a wave function? Let's say with reference to the example that we just talked.
So wave function is so for example, like wave function is not something physical, right? So I cannot measure wave function. Nobody can, right? Because it's a mathematical tool. So we can construct at most probabilities and we can construct maybe density matrices, but really wave function, we can only construct it up to a global phase. Because let us say I have a probability distribution, which actually corresponds to psi, right? Or psi square, right? And so like if I have some psi as a state, then the psi times e to the power I theta also gives the same probability distribution. Right, so up to a global phase, we can sort of talk about the wave function, but you cannot construct the wave function like there is no single answer. That's what I'm trying to say. What we can construct is only a probability distribution, right? And up to a global phase, then we can say that this is the wave function up to a global phase. But multiple global phases could give you the same result. Does that make sense?
Yes, sir. Okay.
Do you have any other question?
Sir, and the state that we get, the wave function that we get, it is common for all the observables.
Yes, the state, by state, what we mean is that using that state. So here is the thing. We can do experiments. What we want to do as physicists here is I can do experiment and I want to make a theoretical framework that allows me to predict outcomes. So for example, if you look at classical mechanics, let's take a step back and look at classical mechanics. I want to make a theory. It is not that people did not know that if you kick a ball, the ball will move. It is not that they did not know it before Newton, right? People know that if I kick a ball, it moves. And if you don't do anything to that, it doesn't move, right? So what Newton came along and did was laid down a mathematical framework so you could predict that if I threw this with this velocity in this direction, where would it land? Right? And I can do an experiment, right? And then see that it does land there. So experimentally, what we want to do is we want to predict different outcomes. So I should be able to predict, let's say in simple projectile motion, if I have some sort of an object and I know with what velocity I'm throwing it, I can predict a lot of things. Like for example, I can predict how long it takes for it to reach the maximum height, right? Time taken to reach the maximum height. I can predict the maximum height. I can predict the range, right? I can predict the range. Like this, I can predict a lot of things, correct? So that theory, that framework of Newton is allowing us, that classical mechanics is allowing us to basically predict these different outcomes which can be measured. So similarly now, when we look at the experiments like, for example, Hitachi double slit experiment or electron diffraction or discreteness of energy levels in mercury vapor, we are seeing some results which are not predictable from classical mechanics. That is, whatever Newtonian mechanics or electrodynamics that we have, they are not predictable from there. So then my goal is to develop a new theoretical framework that can help me predict this. And from what we are developing based on the experiments, again, the emphasis is on based on the experiments, is that we see that we cannot predict individual outcomes. We can only predict statistical outcomes beyond a certain level. Like, for example, if I go to microscopic particles, I'm only able to predict statistical outcomes. For example, like if I prepare in a Hitachi experiment, if I prepare from the same tungsten tip, the electrons are coming, but exactly the same way, but they land up at different places on the detector. So I'm not able to predict exact outcomes of every single measurement, but I can tell you something about the overall statistical distribution. So my theoretical framework, I'm using this wave function or state as a mathematical tool that encodes probabilities for everything that I can measure. Like, for example, in classical mechanics, I can measure maximum height, I can measure range, I can measure time taken to reach the maximum height, time taken to hit the land again, different observables that I can measure. So similarly, what I am trying to do here with the wave function is build a statistical feature, framework that allows me to predict any observable. Like, so this state should have information about, let's say, energy. It should have information about momentum. It should have information about spin. It should have information about position, about everything. Whatever you want to measure, whatever is observable physically, the wave function, the state encodes probability distribution for all the observables. So let's say you want to find out the energy, then what you would do is you would find the expectation value of the Hamiltonian. This gives you the average energy, which I can measure, right? For example, if you want to find the average momentum, then you do this, and I can get average momentum and I can measure that, right? So that wave function should encode information about all the possible observables, not just one observable. Does that answer your question, Satvik?
Okay, sir. Yes.
Okay. Any other questions?
Sir, could you briefly explain the difference between mixed states and superposition states?
We're going to do that today in density matrices. So maybe we'll see if it is not addressed by the end of the day, then we could come back to that question. How about that?
Okay, sir. Sure, sir.
Okay. Any other questions? Okay. In that case, let's proceed. So today we're going to talk about density matrices in quantum information. So far we have used multiple ways to represent the state. Again, the state encodes probability distributions. So one way we did this was on first day, we just kind of called it like psi of RT. And later we saw the Dirac notation psi. And now we are going to look at another way to encode the state. And that is the density matrix. So today, what we will do is we'll define what a density matrix is. We'll talk about its properties. We'll explore pure and mixed states and their connections to state vectors. And we'll discuss convex combinations. And we will also talk about multiple systems. And I have some codes that we can run on Qiskit to see some nice things. We'll introduce reduced states and, like I said, implement all these things in Qiskit. So let us begin by considering a quantum system. Let's call it X, right? So this X, when we say the quantum state, this lives in a Hilbert space, right? And this Hilbert space of like a real system is typically infinite dimensional. But, in quantum information or in some simpler experiments, we're usually interested in only a finite dimensional subsystem. That is, for example, if I'm doing Stern-Gerlach experiment, I am maybe interested in only a finite subset of like maybe just the spin states. I'm not interested in the position or the energy or something else. I'm only interested in spin, let's say, right? So I'm interested maybe only in a finite dimensional subsystem. So like if I have a qubit, it can have 2 states, let's say, or a qubit that have 3 states, or in general, some dimension sigma that is a subset of the infinite dimensional Hilbert space. So in other words, we are abstracting away the infinite dimensionality and we are focusing on discrete labels. That is, for example, when I talk about Stern-Gerlach experiment set up along some axis, it is not that the state is just spin up or spin down. That is not the state. So to say the state is spin up is not appropriate, because that is only a subset state, meaning in the spin part of the wave function, that is up. But the total wave function will be, it's you have to consider psi of RT, which is combined with the spin space, right? So we are only talking about spin space in Stern-Gerlach experiment. So we are abstracting away, like, let's say, forget the position, spatial dependence, or the linear momentum or whatever. We are removing that and we are only considering spin angular momentum, right? So the thing that we are going to do in quantum information and in our qubits is we are going to do the same thing. We are going to abstract away all the things that we don't need and work only with a finite dimensional space. And we are going to label that. So we are going to label those states. For example, in case of the Stern-Gerlach experiment, I can say my subspace is simply up along X or down along X, right? And I can give these labels. I can give this label 0 and label 1, right? Or the other way around, whichever way, right? So I can give them 2 labels. And this label is what I'm calling using a index X. So in general, if I have an infinite dimensional Hilbert space, for any given qubit or qubit or any quantum bit or set of quantum bits, I am abstracting away infinite dimensionality and I am taking only a subset of states which I am labeling by S. So when I say S is 0, I'm referring to maybe 0 state. When I say S is equal to 1, I'm referring to the state 1. Right? So these basis states, these labels we call them as, or in general, they're called as classical states, right? Because they represent the outcomes of a measurement, right? Like when I say 0, that means that it is spin down, right? And it is only a label, it is not the state, right? So don't get confused between the label and the state. So this S without the ket is the label, S with the ket is the state, right? So they basically are providing the label for the state, and we are working with only a finite dimensional part of the subset of the infinite dimensional space. So let's say we have a qubit system, and then I can say sigma is 0 or 1. So the 0 or 1 are labels. So for example, the 0 label could be spin down state. This 1 label could be spin up state. Or the 0 label could be ground state in a harmonic oscillator, and 1 could be the first excited state in the harmonic oscillator. Right, there we are removing all the other states of the harmonic oscillator, or removing all the other states of spatial dependence in case of spin, whatever it may be, right? So for a qubit, you have 2 states, right? It's by definition, qubit is 2 states. So it could be whatever it is. That basis we are referring as 1, 0 and 0, 1. So this could be down spin and this could be up spin. This could be the ground state, first excited state, whatever it is. We are simply representing it as 0 and 1. So these are classical labels which we are using as indices to refer to the system. So when we talk about our quantum system X, the state, again, recall that this quantum state means it encodes probabilities for all observables, not for the subset of the observables, right? So we are trying to describe this using a density matrix. So whatever this density matrix is, here we can define this density matrix for just the subset that we are interested in, or we can describe it for the entire Hilbert space. So for the course in quantum computing and information, we're going to define this density matrix for our subset. So this doesn't mean that we are describing all the observables. So we are only interested in this sub-Hilbert space. So please bear that in mind. So here, because I'm taking only that subsection, only the spin, so here what I'm trying to do is develop this row that acts only on the subset of the total Hilbert space. Is that clear? Any questions? So in general, this density matrix has complex numbers and it's Hermitian, and its rows and columns are indexed by the labels in sigma. For example, let us say I have two states sigma. Remember that two states 0 and 1. That means the sub-Hilbert space has 0 and 1 states, where when I say S is equal to 0, which belongs to sigma, I'm referring to this state 0. When S is equal to 1 in sigma, I'm referring to this state 1, right? So these sigma labels in sigma are corresponding to the rows and columns of the density matrix. In other words, when I write the density matrix row, so this elements, let's say you have 4 elements, let's say A11, let's say A00, right? The 00 is the labels that correspond to the labels in sigma, right? So these 0 ones are what, so I could write this as A01, A10, and A11, something like that, right? So these labels in sigma are corresponding to the rows and columns indexed in the density matrix. So the first property to be a valid density matrix is that it must have a unit trace. By trace, what we mean is the sum of diagonal entry elements. So if I have a matrix that looks like A00, A01, A10, A11, the trace of this matrix A, it would be simply A00 plus A11, the sum of all the diagonal elements, right? Again, whenever you see something like this, trace is equal to 1, right? That means that it should have all the total probability would be equal to, basically it's related to the total probability, we'll see that. And then it should be positive semi-definite. So here rho is a matrix, but we're just indicating as rho greater than 0, rho is not a number. By positive semi-definite, what we mean is that this matrix has all non-negative eigenvalues which are real, right? So all eigenvalues are real and non-negative. So that's what we mean by positive semi-definiteness. So these are two important properties of the density matrix. So before we jump into how to look at the density matrix, I want to talk a little bit about what the trace is and some properties of the trace, which we are going to make use of. So for n by n matrix, right, let's say A is equal to some alpha ij, the trace, like I said, is defined as the sum of the diagonal elements. That is, you're going from the first element to the nth element, and you're just summing up along the diagonal. This trace shows linearity, meaning that if I have two matrices A and B, right, then if I have trace of alpha A plus beta B, then I can write it as alpha times trace A plus beta times trace B, right? So a simple one would be like if you have ABCD, right, then you have AD and 1. So you can prove this more rigorously if you want. It's a standard one in linear algebra. You can use this expression to prove the linearity, but we are not going to do that. So the consequence of this is that recall that whenever we are expressing operators in quantum mechanics, or either it be the density matrix or the Hamiltonian or any matrix, then that means we are expressing it in a basis. So for example, when I say my vector, right, let's say in general, let us say I have some vector V. If I say 1, 2, 3, this vector itself is meaningless without the basis, right? So if this is a vector in 3-dimensional coordinate system, then what this means is it is 1i plus 2j plus 3k. Unless I know the definitions of I, j, and k, I do not know anything about this vector, right? So it is expressed in some basis, right? So the vector, whatever we are looking at, whatever operators or vectors that we look at are expressed in some basis. That basis is not directly seen, but these are just coefficients that are associated with that basis. So the reason we are interested in trace is irrespective of which basis you express the operator in, the trace is going to remain always the same. The trace is basis independent. So if you change the basis, that is, if you change the omega or if you change the sigma, let us say we can have a 0 state and 1 state. This is one basis, let's say. I can build another basis, right, which is also orthogonal. That is, I can build plus and minus state, let's say, which is like 1 over square root 2, 0 plus 1, right? And here 1 over square root 2, 0 minus 1, right? I can build this basis. So I can express the same matrix in either 0, 1 basis or plus minus basis. Then the elements may look different, but if you compute the trace, irrespective of which basis you are in, the trace is always the same. And that's the beautiful thing about trace. It is basis independent. That is because all the eigenvalues of A, right? Trace is the sum of all the eigenvalues of A. So irrespective of which basis you express in, all the eigenvalues are going to remain the same. So trace can also be defined as sum of eigenvalues. So if you have a matrix, you can find its eigenvalues, and it's just a sum of those eigenvalues. So the cyclic property, again, is trace of AB is same as trace of BA, right? Trace of ABC is equal to BCA is equal to CAB, right? So just because the trace of AB is equal to trace of BA, it does not imply that A and B commute. That is, AB may not be equal to BA, right? Only the trace is equal, right? Trace is basis independent and it is cyclic, and the equality of the cyclic property of the trace does not imply that if you operate B first and A next, that is not the same as operating A first and B next, right? So these are some important properties of the trace. And now once we build the density matrix, I still haven't told you what exactly the density matrix is, but the density matrix encodes the same information about all the probability densities of all the observables. It is equivalent to the definition of state, right? Like, for example, if I have psi, right? Whatever I can get from psi, I can get from rho, right? So for example, if I have an operator m, I want to get the expectation value of m, I can get that as psi m psi, right? In case of the density matrix representation, I can just get it as trace of rho times the operator matrix M. So that although we are putting it in a different way, and we will see why this is more advantageous in a minute, but the expectation value, whether you do it as trace of rho M or whether you do it as psi M psi, ultimately these two should yield the same value, right? Just different ways of looking at it. So if we do rho square and the trace of rho square is also equal to 1, then we say that that's a pure state. If trace of rho square is not equal to 1, that is, if it is less than 1, then it is not a pure state. So I think somebody asked a question about superposition and mixed states. So if you have a d-dimensional system, let's say you have a 2-dimensional system, and if the trace of rho square is equal to half, then what we say is you have a maximally mixed state. If it is not half, but it is less than or equal to, it is less than 1, then it may not be a maximally mixed state, right? So that is the difference. So you can tell that from the trace of rho square. But if trace of rho square is 1, then we say we have a pure state. And we'll see why that is in a minute. So we'll stop it. Sorry.
Professor, I have one question.
Yes.
Is there any proof of getting 1 over d as a lower bound of this trace of rho square?
Yes, there is, but we are not going to go through that.
Could you just refer to?
Yeah, so it is there in book by, it's there in any standard quantum book. You can look at maybe something like Shankar, no, not Shankar, maybe you can look at Ballantyne, Ballantyne's book. Huh. It's in Sakurai also. So you can look those up on those two books maybe. Does that answer your question?
Yeah.
I don't know who asked the question.
Yes.
I think. Okay. Okay, great. So okay. So again, going back to the statistical interpretation, this density rho encodes the probabilities of outcomes across an ensemble of identical prepared systems for all observables. It encodes information about all observables. So there was another question that I received by email, which I would like to address briefly here. That is, let us say we have an oven where we are heating silver atoms. So our silver atoms are coming out and I collimate it. And then I have a Stern-Gerlach apparatus that I set up along z-axis, right? And so now if I call just, let's say I call just this part as my state preparation, just silver atoms and this part as my state preparation, right? Just the silver atoms and collimation. Then the state, that state would encode probabilities about all the observables. So if I make a measurement, that is, this is the measurement. If I make a measurement with spin along the gradient set along the z-axis, then what I'm going to get is I would get 50-50 up and down, right? Now, if I repeat the measurement, when I say repeat the measurement, what I mean to say is it is not again a single particle measurement. It is not again single measurement. It is always ensemble. So if you read books like Griffiths, that is very confusing because it talks about probabilities, but it also talks about only single measurement. So it's very confusing. So a single measurement is not a probability distribution. So if you make a single measurement, it's not going to give probability distribution. If you don't have probability distribution, then you do not know the state, right? So now if I combine now the new state preparation, right? That is, let us say I filter out only these particles. I filter out only these particles, right? Then my state now becomes, my state prep becomes this. This whole thing becomes my state prep, right? So now if I look at these things, yes, they will all be spin up along z direction, whatever comes out, but still you do not know the other probabilities about other things. You do not know what is it spin along y direction, what is it spin along z direction. So if you measure spin along y for one particle, you may get it as up. If you measure another one, you may get it as down, right? But all of them would have spin along the z direction. So once you have made the measurement, you have changed the probability distribution in some sense, because now the previous measurement is involved in the state preparation. I think this was Subhanshu who asked that question from Griffith. So I hope that answers your question, Subhanshu. Okay, let's see. Yes, okay. So that's what that's the point that this slide is trying to make, that it is uncodes probabilities of outcome. So whenever you think about single measurements, okay, I'm going to hesitate saying this, but I will say it nevertheless. Just because something is written in a book doesn't mean it is right. And you don't have to trust. You don't have to accept authority. And you need to be original, and you need to think. Just because Griffiths wrote it or Ballantyne wrote it or Einstein wrote it, it doesn't mean it is right. Right. So what it has to do is that it has to make sense. It has to make, don't go by the authority of who is writing it. If somebody from Harvard wrote it, doesn't mean it is true. If somebody from Dharwad in Karnataka wrote it, doesn't mean it is false, right? You have to investigate for yourself. So there are unfortunately a lot of different things that are said, like making a single measurement versus probability. Making a single measurement is not probability. So when I toss a coin, a single coin, when I toss it once, when I say it has a probability of half and half, what I mean to say is, if I toss this coin 1,000,000 times or 10,000 times, half the times I would get head, half the times I would get tails. But a single coin toss is not probabilistic, in the sense that in a single coin is you are going to get whatever result you are going to get. It is not an ensemble distribution, right? So do not think about state in single measurement, because a state encodes information about probabilities. A state does not encode information about single measurements. So to say that a state collapses or something else happens upon a single measurement is not very meaningful, because a single measurement doesn't encode probabilities. That's it. I hope that makes sense to you. Any questions on that? Okay. Okay, that's the single shot measurements here. So here I have a Qiskit code. So let us go to Qiskit code, and what we are going to do is first we are going to generate this. Okay, there's a question I think in the chat. Okay, got it. So we're going to open Qiskit, and what we're going to do is we are going to sort of prepare this state 0 or state 1, or we can prepare plus state. So whenever we are saying we are preparing a state here we are using Qiskit, but we are still not running on a quantum computer. We will try to run on a quantum computer. We can do that. We can run on one of the IBM actual quantum computers, but we'll try to do that later because I have only a reserve set of tokens. So what we are doing now when we run the code is we are running it on a simulated quantum computer. So it's still a classical computer. It's just linear algebra we are doing. But the hope is that the code gives you more hands-on because, we put the hands-on in the course title. So that's what this means, that you're trying to code this and get some hands-on. But you can run this exactly same Qiskit code on an actual quantum computer by adding just a few lines of code where you have to add an API from the actual quantum computer, and it will run it on the quantum computer instead of on a simulator. So here what we're going to do is we're going to do single shot measurement, see what we get, and then we do on a superposition state single shot measurement, and then we will also try to look at multiple measurements. So let me open that. Are you able to see the code? Okay. Oh, okay. Oh, great. Awesome. Okay, let me run this. I should have done this before. So I do hope that all the codes that we are sending, all the files that we are sending, I know that we are doing lectures daily, but please go through those and, please make use of those to understand the material better. And if there are any questions, please feel free to email us or come back here with the questions so that you can benefit maximum out of this course. And maybe, there are some questions that would also be useful to us as instructors and also your peers who are attending the course, that there may be some thoughts that others may not have gotten, right? So okay, so here then what we are going to do is we have imported everything. We are going to get state 0. Before we go there, I think Anuradha had a question a couple of days back. So use this button here. This is an available AI feature. And if you click that, it says like explain the code, right? And if you click that, it will explain the code very well what we are trying to do, right? So let's see whether it does a good job. So I'm going to explain it before it explains there as it is working. So here we are basically generating one state. We can set that to 0 or 1, right? And then by default, it is creating a 0 state in the initial state. You can create this X is a poly NOT gate. So when you apply NOT gate on 0, so the state is by default 0. So even if you don't put this, it's okay, right? The state is by default 0. So to create state 1, what we are doing is we are applying a NOT gate. This poly X, if you recall the poly X gate, that is simply a NOT gate. So I'm going to maybe pull this up here. So poly NOT gate is something like this, right? So this is going to, if you do this on, let's say 1 0, right? Then what you're going to get is 0 and 1, right? So it has flipped from 1 0 to 0 1, right? So this is the X gate, poly X gate. So that's what we are doing here. So if you do the poly X gate, it gives you, flips this to 1. This H is a Hadamard gate. And Hadamard gate also we have seen, right? Hadamard gate basically flips 0 into plus state. So that would be like something like 1 over square root 2. I think it is 1, 1, 1 minus 1, something like that. So let's see. So if I apply this on 1 0, then what I'm going to get is 1, and 1, right? So it's going to give me this is the same thing as plus state, right? So this is the Hadamard gate. So this is applying the Hadamard gate. And then this is basically I'm simulating the whatever, like a quantum computer. I'm not running it on a real quantum computer, and I'm simulating the run, right? And I can mention the number of shots. I can even measure it single shot, or I can measure it 100 shots or whatever, and I can get the results and then plot the result as a histogram, right? So that's what we are going to do. So now I explain the code in words. Let's see whether the Google AI Gemini is explaining that similarly. So it's doing a pretty good job. So state preparation, it is initializing the state into one of these, then it's using the simulator, right? And if you don't understand one of these, then you can say like explain number 4 in more detail, or explain number 5 in more detail, and then it will explain it in more detail, right? So so please use that feature. I think there is a question here. Let's see. Okay, thank you. Okay, so now I made it into shot 1. So let's say I want to begin with state 0. Okay, now if I measure only one shot, what is the answer I'm going to get? Can you please answer in the chat? I'm going to run it once. What do you think would be the, if I start with state 0, right? If it is state 0, we're just going to pass it. So it's going to come here and I'm going to measure it. Am I going to get 0 or 1? Okay, very good. So we see that most of you are answering 0. So let's check. You got 0, right? This is showing this one is not the result. It is showing like we ran the shots one time. Now, if I run again, will I get 0 or will I get 1? Or will I get it? Can I get a different result if I run it multiple times? Let's say I run it 1,000 times. Will I get only 0 or will I get 0 and 1? If I run it 1,000 times, so will I get with 100% certainty, will I get 0? Okay. We have some mixed answers. Some people are saying yes, some people are saying no. We are preparing the state in 0 and I'm measuring the same thing. It is like I'm saying like I'm preparing the state in spin up along Z and I'm measuring spin up along Z. Right? I'm not making a measurement of something else. I'm measuring the same exact thing that I prepared in. Right? So let's see. Let's see. So then you see that with 100% certainty, I get 0. The reason is that I'm measuring the same variable. I'm not measuring something else. So what changes when we say state? The difference is when we say state, it encodes probability of all the things. So the state may have changed, but that particular variable, that particular 0, spin 0, that will be the same. That is here in Stern Gerlach, if I filter out spin up along Z, it is spin up along Z, but it may be spin up along X, spin up down along Y, or it may have different energy and different momentum. So it state meaning and the probabilities of all the observables may change, but that particular observable will remain the same. Am I making sense? Okay. So then let's see what happens if I set it to state 1, right? Then also we are supposed to do the same thing, right? State 1. So then again we'll get with 1,000% certainty. Not 1,000, 100% certainty all the 1,000 times we get the same value, which will be 1. Now let's say if I instead use plus state, I used plus state, right? Then I want to make it measurement 1. So what will I get now? I'm making my state plus, so and I'm going to do one shot. Will I get 0 or will I get 1? Can you know before? superposition of 0 and 1. No, but I will get only one result, right? Again, you're going back to cat being alive and dead. Cat is either alive or dead. You should get one of those, right? Whatever it is, you should get one result, right? So you will get one result. So what we got is 1. Now, if I run this again, will I keep getting the same result? Will I get 1 again if I run it again? So so let's say, so now I got 0, right? So if I make multiple measurements, right, then I may get different results. So now if I run it 1,000 times, then I may get a probability distribution, right? So you see, I'm getting 500 times 0 state and 494 times down state. Is that making sense? Any questions? Okay. So then let's look at measuring in different bases, right? So here what we are going to do is we are going to prepare our state. So this is again, I want to help you understand or visualize state preparation and measurement. So this part of the code is just preparing the state, and my state I'm preparing is plus. So again, by state, what do I mean? I'm encoding the probabilities, right? So my probabilities are encoded in that. Here I'm looking at a subset, right? Because we cannot really look at infinite dimensional space. What we are looking at is just, let's say for our qubit, 0 and 1 state. So I'm preparing the state in plus state. And as we have seen from the previous run, this plus state is simply 1 over square root 2, 0 plus 1. So it is encoding the probability distributions. That is, I should get 0 state 50% of the time and 1 state 50% of the time. That is the, those are the probabilities that I am encoding, right? But these are along one direction, right? So it could be like, let us say, spin up along X and spin down along Z. Along X, right? So my plus along state could be 1 over square root 2 spin up along X plus spin down along X. So this one is giving me only probabilities along a subset of the infinite dimensional space. So truly it is not a quantum state in the sense that we are not encoding, we are only taking that subset. But truly it is not a true state in that it is encoding all the probabilities. So here we are just preparing a state, filtering out something like this plus state. So then, and then what we are going to do is we are going to measure this in X basis. All right. So measure plus state in X basis. That is the, so we are preparing in X basis. That is, we are preparing plus X and minus X. So we are preparing this state, right, that you see here, plus state. And then first I am going to measure that in X basis only, right? And then I'm going to plot the histogram. So for this part 1, when I measure this like 1,000 times or 1,000 particles, right? So let's say I have some state prep, right? And this state prep is giving out some particles, which I say are prepared in this plus state. So now, if I measure 1,000 of these particles, 1,000 particles, right? What am I going to get? The histogram. Am I going to get just spin up or spin down, or what am I going to get? Hello? Are there any? Yeah, we do not know because before itself we cannot say anything about the positive state, right? And then following that, I'm going to measure in some other basis. I'm going to apply y basis, and then I'm going to do z basis. So I'm going to look at x, y, z basis, just to show you that this really is not a state. Because when we talk about plus, we're only talking about x. We're only preparing, when we filter with Stern-Gerlach, we're only talking about one part, like spin up along x or spin down along x. We're not really talking about all the bases, x, y, z basis. I hope I'm making sense. So let's see what happens when we run this. So I prepared all the particles in spin up state. right? So when I measure the spin up state in X basis only, right? It is giving me all 1,000 runs are giving me the same value in that basis. Are you with me? So for example, if I used a Stern-Gerlach experiment along x-axis, and I just pull out only these particles that are coming out of here, I measure this along spin up along x 1,000 times, I'm always going to get spin up. Are you with me? But that's only because I have measured only spin x, right? But this spin x is not a state. That is the thing that I want you to understand. It is not a state because it doesn't give you any information about other probabilities. Are you with me? Okay, so there is a question about quantum circuit, what the quantum circuit does, right? Quantum circuit, where is the quantum circuit? So basically, what this quantum circuit means is that it has two arguments. The first argument is the number of qubits you want. So here we are talking about 1 qubit, right? And whatever measurement you make, you want to store. Oh wow! So it's talking about these things, right? So it is the number of qubits, and this is a classical register. The second part is a classical register. So whatever you measure on this, you're going to store on that, right? So you can have, if you want to make 1 qubit and 1 measurement on the qubit, you can put this one. If you want to make 2 qubits, you can change this to 2, right? So let me see if AI can answer this. So essentially, Subhanshu, that's what is happening, that it is, okay. Yeah, okay. So you see, if you did like that, for others who, if you don't understand the code, you could do that. You can just ask that. So the first argument specifies the number of qubits, and the second argument specifies the number of classical bits in the circuit, right? So, and so the qubit is what you're measuring, and the classical bit is used to store. Here in this code, it really doesn't matter, because truly in this code, both are classical bits only, because we're just simulating. When we run on an actual computer, it would matter, right? Can we say it is a substate? Yes, it is a subspace, not a substate, but a subspace. So what we can say is, we are taking, like, out of the entire big Hilbert space, we are only considering, like, let's say HX, the subspace of that, right? Okay, so we ran this. So we first measured in X only, then we get every time the same thing, but you measure in Y basis, you get half and half. You measure in Z basis, again, you get half and half, right? So here what we are doing is, I am not making subsequent measurements. I'm just making measurements in different bases. That is, I have filtered out, I have prepared one state. My state preparation technique is Stern-Gerlach along some, my state preparation is silver atoms are coming out, and I have Stern-Gerlach along X, and I cut a slit out of the top portion. And so this is my state prep. This entire thing is my state preparation, right? So whatever particles are coming out of here, if I measure them again in SGX, then of course I know that I will get spin up. Now, if I measure these in SGY, then I get half the time spin up and half the time spin down. If I measure them in SGY, right, I get half the time spin Z, half the time spin down Z. That is what was the code that was showing, that if I measure, this is the state preparation and this is the measurement part. In the measurement part, I can pick what I want to measure, right? If I measure spin along X, I would get up. If I would measure spin along Y, I do not know. I may get up or down. If I measure along Z, I may get up or down. That's what that code is showing. The next part of the code is, we want to make subsequent measurements. That is, I want to measure spin along one direction, then I want to make a subsequent measurement. So here I am measuring only one thing at a time. So I used, Subhanshu, again, going back to your question, I'm measuring only one thing, right? I'm measuring only one thing, but multiple times. That is, I'm only setting up SGX, but I'm measuring SGX multiple times. So I need only one classical bit to store. I'm not measuring two things simultaneously. If I measure, let's say, SGX and SGY simultaneously, that is, I measure SGX first and then measure SGY on top of SGX, then I need to change this to 2 bits because I want to store first whatever came out after SGX, I want to store that in the first bit, then perform SGY and store the result in the second classical bit. So this second argument, even if you have only 1 qubit, you could have 2 classical bits or 3 classical bits. That is, if you are performing successive measurements, then you can store each result in that classical bits. I hope that helps in understanding what that quantum circuit is. Any questions? I think there's a question in the chat. Okay. IPSA, was that a question? Is that a smiley? Okay. If that's a question, okay. How do we understand code so fast? Okay. I'm sorry that I'm sort of going too fast in the code because this is only a 10-day course, but you will have access to the code and you have access to Gemini AI, like I showed you. So you don't have to understand it like right now, but maybe you can spend time later and understand it. But unfortunately, we will not be able to like go slowly because this is only a 10-day course, right? So we're already actually lagging behind. So that's why, like Python and some of this linear algebra was a prerequisite. But I think, I'm asking, how do you understand the code so fast? Because I wrote it, right? So I wrote the code, right? So but yeah. So let's see the subsequent measurements. So this is the subsequent measurement. So we are preparing in spin down state. So this is like, I'm saying I am extracting spin down from Stern-Gerlach along X. Then I am first going to measure along Z axis, make some measurement, right? And then store that in the first classical bit. So here, notice that I initiated 2 classical bits, 1 qubit, but 2 classical bits. So I'm going to make measurement on 1 qubit. The first measurement I'm going to store in the first classical bit. The next subsequent measurement I'm going to store in the second classical bit. So now the question is, I prepared this state. So I have Stern-Gerlach X, and I cut at the bottom here a slit, and then this is my state preparation. So I'm getting spin down state along x-axis. So this is my state prep, right? So measurement 1 I'm going to do is apply Stern-Gerlach along Z. Then whatever comes out, I'm going to measure second measurement on the same particle, measure 2, Stern-Gerlach along again X. All right. And then you can also try swapping this, right? You can also try swapping this. You can measure Stern-Gerlach X and then Stern-Gerlach. So this part is the preparation part. So this part is the preparation part. And this is measurement 1 and this is measurement 2, right? So for measurement 1, this is the state preparation is in the blue rectangle, right? For measurement 1, state preparation is in the measurement number 2. For measurement number 2, the state preparation would be this, right? That is, you prepared the state, measured Stern-Gerlach along X, and then you are measuring Stern-Gerlach along Z, right? So then you are going to store that in the second one, right? So and then we are going to do this like on 1,000 particles. That is basically I'm going to get, I prepared the state, meaning that, silver atoms are coming out. One silver atom comes out. I make the first measurement on that silver atom along Z axis, then make along X axis. Store that in classical bits, then measure the next one, then measure the next one, so on and so forth. I'm going to repeat that 1,000 times, right? So then what is going to happen is we are going to plot whatever we stored in C0 classical bit, that would be the results of first measurement. Then I'm going to plot whatever I get in classical bit 1, that is the second measurement. Am I making sense? 250 should come out of the second measurement. Okay. Priyanshu's answer is 250, but we are going to measure it 1,000 times. So like, let's say 500, right? Because I'm counting only 1,000 particles that have spinned up. So you don't need to include the factor of half. So what do you think, others? Priyanshu thinks 250 would come out after the second measurement. So what I want you to write is, what would you expect for, if I make 1,000 measurements, what would you expect C0 values would be? So C0, so I have 1,000 C0 values and 1,000 C1 values. So I can plot the histogram of these values. So if I plot the histogram of C0 values, what would you think? Would it all the 1,000 times be 0 or 1? Did you understand the question? Are you guys with me? Okay. If you understood the question, please answer in the chat what you expect for the statistics of C0 and C1. Do you expect C0 to be always the same, or do you think it will get 50-50, or what will happen? Can you? Okay, 50-50 for C0. What about C1? Okay, so let's run it. Let's run it and check. Right. So first Z, then X, right? So if you do first Z, then X, right? You get excuse me, Z only. After C0, you get 0,000 times, because I am preparing in this spin down state. I'm measuring the same spin down state. So if I measure the same spin down state, I get 1,000 times. But if I measure after measuring Z, I get half and half, right? Because for this, the preparation is the same. Immediately after this, I will get the same result, right? But if I measure along X, then I would get different results. So let's see here. I am preparing the first measurement. Let's say now measure in Y basis. So this measures in, so prepare this in 0 state. So let's say I remove this part. I'm not going to rotate to the X basis. No, sorry, that was wrong. I prepared it in the Z basis. It is by I made a mistake there. I prepared it in Z basis here, because by default it is in the Z basis. So I am going to put here, let's say I put a hash here, so that is not going to go. So I prepared it in the Z basis. I'm going to make the first measurement in the Z basis. Then the next measurement also I'm going to make in the Z basis. I'm not rotating, right? Are you with me? I'm making the first measurement in Z basis, second measurement also in Z basis. What would we get? I prepared the state in Z basis, and I prepared, let's say, spin down along Z basis. And then, so this is my state prep. Then I'm going to measure in SG along Z first measurement and SG along Z in the second measurement. Okay, 100%, right? Same. Let's see. We ran it. So let's see. Yeah, that's right. So I get 0 and 0, right? Same thing. So if you measure spin, if I prepared it in, if I say if I'm getting spin down along Z, if I measure spin down along Z, yes, you get the same result only for that Z, right? But if you measure that along another axis, right, then you don't get the same result. Then you get 50-50 probability, right? So that's why we do not say that after I have made the first measurement, right, that I still have the state information. That doesn't encode the state information. All that repeated measurements will give me is, it will tell me about what I already prepared it in. It won't give me information probability about other probabilities about other states. I hope you guys are able to follow what I'm saying, right? So now let's say we rotate it again and measure, right? So we can just copy paste this, and okay, but we need to make, oh, okay, it's already 4:20, so we'll stop here for now. When we come back, we will talk more. What do we measure? Why do we need to measure a state different basis? What do we measure by measuring a state in different bases, trying to get the intuition? Yeah, good question, Saptagiri. So basically, when we talk about a state is encoding information about all probabilities, about all observables. That means the state should have information about what will happen along x-axis, y-axis, and z-axis. Otherwise, it is not a state. If I have information only along x-axis, then that is a subspace. If I have information along only y-axis, that's a subspace. But I need information along all x, y, and z. Not exact outcomes, but the probability distributions along each direction. That is what we call as the state. So by measuring, if we want to, like, for example, if I have a qubit, I do not know what the state is, and I want to map the state, then basically I have to take that state, make multiple identically prepared systems, and then measure it along all the different bases to get the full state. Does that make sense, Saptagiri? Okay, great, awesome. Okay, thank you guys. And so we will come back, we will stop here, and we will come back and talk more about density matrices. And then I want to talk about more interesting things. I hope we can go faster in terms of Bell states and entanglement. There is a lot of exciting stuff coming up. And then we will also talk more about density matrices. Okay, thank you guys. See you at 4:50. So we will come back at 4:50. 450. So please be back by 450. Thank you.